In mathematics, the affinely extended real number system is obtained from the real number system by adding two elements, plus infinity and infinity. These new elements are not real numbers. It is useful in describing various limiting behaviors in calculus and mathematical analysis, especially in the theory of measure and integration. The affinely extended real number system is denoted or infinity plus infinity or infinity plus infinity. When the meaning is clear from context, the symbol plus infinity is often written simply as infinity. Motivation. Limits. We often wish to describe the behavior of a function, as either the argument or the function value gets very big in some sense. For example, consider the function. The graph of this function has a horizontal asymptote at y equals 0. Geometrically, as we move farther and farther to the right along the axis, the value of approaches 0. This limiting behavior is similar to the limit of a function at a real number, except that there is no real number to which approaches. By adjoining the elements and 2, we allow a formulation of a limit at infinity, with topological properties similar to those for. To make things completely formal, the Cauchy sequences definition of allows us to define as the set of all sequences of rationals which, for any, from some point on exceed. We can define similarly measure and integration. In measure theory, it is often useful to allow sets which have infinite measure and integrals whose value may be infinite. Such measures arise naturally out of calculus. For example, in assigning a measure to that agrees with the usual length of intervals, this measure must be larger than any finite real number. Also, when considering infinite integrals, such as the value infinity arises. Finally, it is often useful to consider the limit of a sequence of functions, such as without allowing functions to take on infinite values. Such essential results as the monotone convergence theorem and the dominated convergence theorem would not make sense. Order and topological properties. The affinely extended real number system turns into a totally ordered set by defining for all. This order has the desirable property that every subset has a supremum and an infimum. It is a complete lattice. This induces the order topology on. In this topology, a set is a neighborhood of if and only if it contains a set for some real number, and analogously for the neighborhood sieve, is a compact Hausdorff space homeomorphic to the unit interval. Thus the topology is metrizable, corresponding to the ordinary metric on this interval. There is no metric which is an extension of the ordinary metric on. With this topology, the specially defined limits for tending to n, and the specially defined concepts of limits equal to n, reduce to the general topological definitions of limits. Arithmetic operations. The arithmetic operations of can be partially extended to as follows. For exponentiation, see exponentiation #limits of powers. Here means both and, while means both and. The expressions and are usually left undefined. These rules are modeled on the laws for infinite limits. However, in the context of probability or measure theory, is often defined as. The expression is not defined either as or, because although it is true that whenever for a continuous function it must be the case that is eventually contained in every neighborhood of the set, it is not true that must tend to one of these points. An example is algebraic properties. With these definitions is not a field, nor a ring, and not even a group or semigroup. However, it still has several convenient properties, and are either equal or both undefined, 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 and are equal if both are defined, if and if both are defined, then, if and then if both are defined, then. In general, all laws of arithmetic are valid in as long as all occurring expressions are defined. Miscellaneous. Several functions can be continuously extended to by taking limits. For instance, one defines etc. Some discontinuities may additionally be removed. For example, the function can be made continuous by setting the value to fr, and for n. The function cannot be made continuous because the function approaches as approaches 0 from below, and as approaches from above. Compare the real projective line, which does not distinguish between n. As a result, on one hand a function may have limit on the real projective line, while in the affinely extended real number system only the absolute value of the function has a limit, e.g., in the case of the function at, on the other hand, and correspond on the real projective line to only a limit from the right and one from the left, respectively, with the full limit only existing when the two are equal. Thus n cannot be made continuous at on the real projective line.